So let's do an example problem with our new version of the ideal gas law. So here's our problem. We have a 1.53 mole sample of a gas which has a volume of 20.1 liters at 25 degrees Celsius, and let's put a degree sign, and 1,415 torr. What will be the pressure of the same sample of gas if its volume decreases to 12.7 liters and its temperature increases to 55 degrees Celsius? So using the guess method, we're going to write down what's being given to us, and we have a lot of things going on in this problem, so a lot to write down. So let's start off with 1.53 moles. So I'm going to write that down. N is equal to 1.53 moles. And since things are changing in this problem, I'm going to write N1 because that's our initial number of moles. Then I go to my next given, which is 20.1 liters. Again, since things are changing, I'm going to write V1, and that's 20.1 liters. Next we have temperature, and that's our initial temperature. It's 25 degrees Celsius. But remember, in all of these equations for gas laws, we need to convert into Kelvin. And so 25 plus 273 gives me 298 Kelvin. It's a good habit to get into changing that to Kelvin right off the bat. And then our last thing is pressure. Our pressure is equal to 1,415 torr, and that's our initial pressure. Now things start changing in the next part of the problem. What will the new pressure be? The volume decreases, so new volume, new temperature. So things have changed, so I'm going to write down what these new changes are. But one thing that didn't change is that since it's the same sample, our moles did not change. The number of moles that we have is exactly the same, 1.53 moles. The volume did change. The volume decreased to 12.7 liters, so I'm going to write that down, 12.7 liters. The temperature changed to 55 degrees Celsius. And remember, we need to change that into Kelvin, which is 55 plus 273, which gives us 328 Kelvin. And then our last thing is pressure, which is our unknown, because notice the problem is asking what will be the pressure. So our unknown, which is the U in gas, is the pressure. So now we've extracted all the information that we can from the problem. So let's look at what gas law we're going to use for this. And of course we're going to be using the ideal gas law, but kind of the new version of the ideal gas law. And let me show you how this is going to work. The ideal gas law says that P1 V1 over N1 T1 is equal to P2 V2 over N2 T2. And so you'll notice that because N1 and N2 are exactly the same value, if we plug those values into this equation, the N1 and the T1 would actually, the N1 and the N2 would actually cancel out. So in this problem, N1 and N2 are irrelevant. And that's true with any time we're solving these problems where we have changing conditions. In the ideal gas law, you simply cancel out what stays constant, because it will be the same value on the left side of the equation as the right side of the equation. So we can ignore it. And that's where the beauty of this form of the ideal gas law comes into play. Because you'll notice that once we cancel out N, we're left with the combined gas law. P1 V1 over T1 equals P2 V2 over T2. But I didn't have to know the combined gas law to solve for this. And that's true for all the different gas laws we've learned. When you cancel out units on the left and the right, we're left with one of the gas laws that we previously learned. So if you know this one form of the the ideal gas law, then you know all the gas laws that we've talked about up to this point. So now we have the units that the variables that we were given up here in the problem. And so let's go ahead and solve this problem by substituting in, which is the S in the first S in gas. So we're going to substitute in the pressure. And because we have torr on the left, we'll end up with torr on the right side of the equation. So pressure 1 is 1,415 15 torr. And we're going to multiply that by the V1, which is 20.1 liters. So I substitute that in, 21.1 liters. In the denominator, the N had already canceled, so we're just going to substitute in our Kelvin value of temperature, which is 298 Kelvin. And we're done with the left side. Now on the right side, pressure 2. That's what we're solving for, so I'm just going to go ahead and put in that variable. We multiply it by our V2, which is 12.7 liters. And we're going to divide by our temperature 2, which is 328 Kelvin. So now we've substituted in every value. The next thing that we need to do is simplify. We need to simplify this equation so that we can solve it. And notice on the left-hand side there's no variable, so we're going to simplify all the numbers over here. And on the right side we have 12.7 and 328, and so we can simplify those. We also can simplify units. I have Kelvin on the left, and I can cancel with Kelvin on the right. I have liters on the left, and I can cancel with liters on the right. And like in our last example problem, the only unit left is a unit that we're looking for, pressure. And that's good. It has to end up that way. So let's go ahead and simplify. 1,415 times 20.1 divided by 298, and that gives us a value of 95.4412, etc., 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 and the unit left is torr. We'll use significant digits at the end, so we're going to just leave it in this number for right now. On the right-hand side, we still have P2, and we're going to go ahead and simplify 12.7 divided by 328. And when you do that, you get 0.0387, etc., etc., and there's no units left, so we're not going to put any unit on that. So I'm going to keep the full number on my calculator so that I can solve for the correct answer. And now we need to isolate our variable, P2. So I'm going to divide 0.0387 on the right, and 0.0387 on the left. And so when we do that, we will get our final answer. So we're solving for P2. And our final answer is 2,464.938, etc., etc. And of course, we need a unit on that because there can be no naked numbers, and our unit is torr. Now we need to figure out significant figures. How many significant figures are we going to round this to? So to do that, we need to go back to all the numbers that were given to us and find out what number has the least significant figures. And so 3 here, 3 here, 3 here, 3 here, 3 here, and 3 here, they all have 3. So our final answer should end up having 3 significant figures also. So when we round this, we're going to round it to 1, 2, 3 significant figures. So we're going to round that 6 right there. So 2,400, and the 4 rounds it down to 6, and 60 torr. So our final answer is right here. 2,460 torr. So that's a great practical example of the ideal gas law in changing conditions, and I think that you'll find this is a very useful formula in solving all these gas laws.